Section 2 gets into the periodic table. This is probably my favorite part of all of atoms and elements themselves, is the periodic table, and it is organized into different groups. I will say that there are different numbering systems, and it comes from where it originally originated. Dmitry Mendeleev kind of had two columns overlapping. It turns out that these tend to be given things like 1b and 2b and 3b, etc. It turns out there's even a block in there that was 3 blocks together were a single number. I think they were over to the right a little bit there, but it doesn't matter. And to make things even more confusing, in America we did one thing, and in Europe they did another thing, where the one group called the A's the ones on the outside and the B's the ones on the inside, and the other one just went 1 A to 8A, and then over here started 1B and went on, and these were all B's here. Unfortunately, there will be places where you still see those old group numbers, and so they exist. Modern International Union of Pure and Applied Chemistry, the group that's kind of in charge of these things, just numbers the columns 1 through 18. I will point out, however, you'll notice there are the 2 missing rows. Those 2 missing rows are usually indicated there somehow, that they're down here underneath. There's supposed to be 14. A lot of them will include 15 because they'll actually take the 2 that belong here and attach them to the group and have a gap here of some sort. But those 2 rows actually get inserted in between there. Those columns are unnumbered. We mention them by their row, but we don't actually number those columns separately. And the main reason that we separate those columns is space. This prints on a page much better than the full periodic table, where you have to go really tiny font if you want that many things written together there. It organizes them in order of increasing atomic number. That statement there is just flat out wrong. There are a few exceptions where it doesn't go up by mass. Now, when the periodic table was originally developed in 1869, Dmitry Mendeleev did arrange them according to atomic mass, and he decided to start a new row instead of just having a giant table or a giant row as had been done before, based off of the mass. He started to notice that there were certain properties that repeated, and so then because those properties repeated, when he got through all the patterns of the properties and the properties started to repeat, he started a new row of the periodic table. And the rows officially are called periods, and that's because the patterns are the same in them. And if you want to be picky, it's actually the periodic table of the elements. I'm not going to say it that way most of the time, but I do want to mention it here. Periodic tables just means repeating pattern table. And there's all sorts of other repeating patterns that exist in things that are organized in tables where those patterns repeat. However, it's frequently shortened to periodic table, and I think almost everyone knows what you mean when you say that you're referring to the periodic table of the elements. Mendeleev wasn't the first person to make a table or to try to arrange the elements, but he was tired of constantly having to buy a new periodic table. More specifically, he was a college professor, and he was annoyed that his students had to keep doing that because printing was still expensive at the time, and so it was just this unnecessary burden on them. And so he decided that he was going to see if he could come up with one that was better. And what he noticed is there's places where the pattern didn't fit. And rather than saying, you know what, I'm going to try to make it work as many had before him, he said, what if we haven't discovered that element yet? And so he left gaps on his periodic table, blanks that could be filled in later on when the elements were discovered. Also, one of the examples there was what he called eka-aluminum, literally just meant underneath aluminum, and it turned out to be an element that we now call gallium. But if it's similar to aluminum, that now tells a chemist what they should be looking for, where they should go look to find this element. And so that was a huge advantage. Not only that, but he also predicted some of the properties. And so it wasn't just, oh, there's an element, and if we find one, well, we can randomly plug it into his table. No, he predicted properties. And it turns out that those properties are based off of the pieces that the elements are made up of, the atoms are made up of. And we didn't know about those pieces at the time. Had we known, it probably would have changed it. It would have been obvious where the gaps are. We are certain that there are no elements before 118 that work. There are other arrangements out there that some people will do because they emphasize other patterns, but the periodic table itself, we know for certain there's not like we're going to have to revamp it and shove an element in here, for example. It's just not going to happen. Anyway, as I mentioned already, you could see the separate numbering here. This one has the B's in the center, and you'll notice it starts at 3, which continues the numbering from there, but 1 and 2B are way down here. That, again, comes from the fact that Mendeleev had a periodic table that was only 7 or 8 columns wide and had a lot of those elements together. He had, for example, copper, silver, and gold in the same column as this column here, the alkali metals. And later on, we realized, wait a second, those should be separated out into 2 groups. I do want to point out, just because I love the periodic table so much, that these 2 rows actually go there. And they have what's called the lanthanum-actinium mistake here. Lanthanum and actinium actually go here, and it's lutetium-lawrencium that go into these 2 spots here. And so you have to imagine this whole thing being shoved to the left, and this end being what goes up into the gap there. Now, I'm not going to test you on something like that, and you'll see the lanthanum-actinium mistake everywhere, but the split is between column 2 and column 3, and not between columns 3 and 4 as they have it here. They have here what some of the what are called family names, and we'll get into those here in a bit. Also, the kind of your large general groups, the metals, the nonmetals, and the metalloids. You'll notice there's one non-metal way over here, although hydrogen sometimes behaves like it's a metal, which is weird because it's a gas, but we'll get into all that soon. So on the periodic table, they're arranged according to similar properties into vertical columns that we call groups. Sometimes those will be called families. The rows are called periods. I found that students frequently don't know the difference between a column and a row. And so the way that I think of this is I think of things like Greek and Roman times where they had those giant fancy columns holding up their buildings and their temples. And I know that those are columns. So, columns must go up and down. Rows is a little bit simpler. If you're looking at stadium seating, the rows go horizontal, and then changing what row you're in would be changing what column you're in. And then we just start from the top and work our way down. I have seen some upside down periodic tables. There's good chemical reasons for doing those. The downside of that is we tend to read from left to right, top to bottom, not tend to. That's how we do it here in America. And so then because we read in that order, it would probably make sense to stick with that order when it comes to writing the periodic table. Your periods are your rows, and your first row has just 2 elements. 2 and 3 then have 8 elements apiece, it turns out, and then the rows after that all have 18, although technically speaking, those 2 rows that stick into periods 7 and 8 make it so that you have an additional 14 elements in there and 32. It'll make sense later on as to why there's gaps like that in the periodic table, but there you have it. Groups are the vertical columns, and as it says, they can be numbered 2 ways, at least here in the States, where we have numbers 1 through 18, which is just the simpler way to do it, but because you'll see the old style out there, your elements in the outer columns used A's, and the inner columns, what are called the transition elements, called B. Now, I'll be honest, I've never heard this representative elements term outside of your textbook, but sure, there you have it. So you know what they're referring to. And some of those groups have names for the groups. I will point out, even though it says there's no common names, I should say there's no common names in the U.S. It turns out in the rest of the world, there are names for these. These are the pnictogens and the chalcogens, and I think this is just called the boron family and the carbon family. And of course, you could call this the nitrogen, oxygen, fluorine family. They're just not there. We don't tend to name those, and I will say that things are awkward because of that stair-steppy line that you saw a moment ago, and there's debate in terms of how the stair steps actually go. Some groups will do them differently, but elements on either side of that, and again, there's some debates about which ones actually belong or not, are called the metalloids, and so nothing in the column is the same until you get down here to the halogens. As far as we know, the halogens is a continuous column, and same thing with the noble gases. It is possible the stair-step line continues on down from there, but even so, I think these old names are going to stick. Anyway, the first 2, you have the alkali and alkaline earth metals, and then the last 2, you have the halogens and the noble gases. You need to know those 4 just flat out. It takes memorization. I'm sorry. Now, the difficulty becomes the two here that have the very similar names. And the way that I have learned it, it's actually something that a student came up with that helped me learn it, because I'll be honest, when I was a student, I took the gamble as a 50-50 shot as to which one was which. But if we ignore the word metal here, then alkaline has 2 extra letters and an extra word, 2 words making up the name, and it's in the second column. Whereas alkali metals is a shorter name and has only the 1 word. Again, we're dropping the word metals, and so here you have the alkalis and the alkaline earths, and so then that's usually enough for students to memorize them. Since Al is aluminum, I tend to think of these as AK and these as AE for those. But you do need to know those 2. They are the tricky ones. Hopefully that little hint helps. This one here then just lists them by name or by symbol. You can take a moment and jot that down if you want, but I think it's easier to label it directly on the periodic table. And then here we just go through showing you them. So here are some of the alkali metals, some of the halogens. They don't show you some of the noble gases. They're all clear gases, so they're not that exciting. You have to trust us when we tell you. The alkaline earths, I don't know why they don't take you a moment to show you there. Anyway, from here, I've got a tiny periodic table just so that I can kind of show you how to do this. But group 7A or 17, that's way out here. And so it's going to be one of the halogens of period 4. One thing to be careful with is period 1 is this first row where there's a gap. So we're actually going to start here with fluorine being period 2, 3, 4. That's going to be bromine right there. 2A period 3, 1, 2, 3. That's magnesium right there. 15 and 2, 15 and 2. That's going to be nitrogen right there. And 6 and 4, 6, and we're already at 1, 2, 3, 4. So that's just going to be the first one in the column there, chromium. Pretty straightforward. To be honest, pinpointing it by a coordinate number like that, sure, it's worth knowing, but it's not something we're going to use often later on. The columns more so than the rows. It comes up a little bit, but it's not something we're going to use a lot. Anyway, there's usually a heavy zigzag line. It's usually in bold. It does not necessarily go down over the whole time. Like I said, we're not exactly sure which ones belong within this group and which ones don't. There's some debate on it, but those tend to be called the metalloids, and that means kind of like metals, but they separate the metals for the non-metals, and they have properties that are both like the metals and non-metals, which is why they're classified as that. I will say more and more I'm seeing periodic tables that do follow the down over zigzaggy line, but there are some where the zigzag is slightly rearranged, where they'll go down twice before going over. And you'll notice here that we don't have aluminum within our metalloids. Aluminum is clearly a metal, just behaves like a metal. Couple minor reactions maybe where that's an exception, but overall aluminum behaves like a metal. But beyond that, it's pretty much elements to either side of the stair step are considered the metalloids. We're less certain of the man-made and the rare radioactives, that they actually belong in the metalloids, and so that's part of why you'll see different stair-steppy lines. We'll stick with this one. Anyway, most metals are shiny solids. Your one exception is mercury, that is a liquid. You can, of course, solidify mercury. You can solidify any element or melt and turn into a gas in the element. They are described as being malleable and ductile, which is just a fancy way of saying bendy. However, ductile refers specifically to being able to be pulled into wires, and malleable means that we can hammer it out into flat sheets. I kind of think of this as being able to make it go almost one-dimensional and make it go two-dimensional. Of course, there's 3 dimensions on everything there. They are good conductors of electricity, and I'll add on to that, good conductors of heat as well. They tend to have higher melting points, and it also turns out then higher boiling points. One thing I will say is a lot of students think of them as hard. That is not the case. The alkali metals are all soft enough that you can cut them with a knife. If you have me live, I'll do it as a demonstration. I'll prove it to you, and they're absolutely fascinating. They're metals that react very quickly. They're soft enough to be cut with a knife, and they react with water to the point where usually they produce enough heat they actually catch on fire and sometimes even explode in water. So So they, not all metals are hard. Those transition metals in the center are. You'll notice a lot of the common metals you're familiar with are in there. Aluminum, lead, tin are not. They're softer metals. They're much easier to bend. They're over there close to that stair-steppy line, and that's part of why they're getting a little bit less metal-like, if you will. Non-metals are pretty much the opposite of metals. They do include hydrogen up there, and they are the opposite. And so they are not shiny, or the probably proper word for that is dull. They are not ductile. They are not malleable. That is, they are not bendy, or the better word for that is brittle. They are poor conductors of heat and electricity. And you'll notice they remember to include heat there. And they typically have low melting points, again, low boiling points, and low densities. In fact, you'll find quite a few of them are gases because their melting and boiling point are so low. And I'm actually going to add that on here because so many of them are gases. There are exceptions. Carbon is a great example of that, being an exception for the boiling. I don't know what sulfur's boiling point is. I know it melts pretty low, but anyway, a lot of them are gases already. If it's a gas at room temperature, it's because it's already melted and boiled. Now, it didn't necessarily start out as solid because Earth isn't that cold, but the point being that it's a gas because it's already gone through those phase changes. And if we try to make it not a gas, it would go through those phase changes under normal room conditions. As I mentioned already, your major exception for the metalloids is aluminum. Otherwise, if they're touching the zigzagging line, we're going to consider them metalloids, and they have properties that are typical of both. A great example is silicon is super shiny but brittle, and it's a good conductor under some conditions. It's part of why we use them to make semiconductors. You'll sometimes hear the group referred to as the semi-metals, or even semiconductors. Semiconductors is a bad name for the group, but we can make little changes to them that make them good conductors, or the opposite of a conductor, an insulator, which I did not mention back here, and I'll back up and mention that real quick, that the opposite of being a poor conductor is a good insulator. It also therefore means that metals are poor insulators. Here then is a table just comparing some properties of a representative element out of each group. Take a moment and read it if you are interested. Here, just identifying them. Sodium is a metal, and just to be clear, metal, non-metal. I suppose I'm going to have to go metalloid, something like that. So non-metal, boron is a metalloid, manganese is a metal, and carbon is a non-metal. I didn't remember to pull over a periodic table for this one. I happen to know it because I've been studying this stuff long enough. But the metals in group 14 are those two. The metals are to the left of that stair-steppy line. These are your non-metals, and this is a mix of the non-metals and the metalloids there. And actually 10 is there, so a metal. The non-metals in group 15, that would be these. These down here are the metalloids followed by a metal. And here you have your non-metals, as we just answered there, and then the metalloids again. The metalloids in group 14, well, I kind of labeled those up here, but your metalloids are those two. This one here includes a non-metal, and then the metalloids, and this one here includes the metals and the metalloids. If you go on to take 111, we get into this more, but in Chem 111, we kind of study organic chemistry, which are the ones that make up living things. There's also areas of organic chemistry like making plastics where they're also carbon compounds, and so it gets lumped in with organic chemistry even though it's no longer solely just living things. But there's about 20 elements that are essential for all life. You have your body, 96% of it is made up of just oxygen, carbon, hydrogen, and nitrogen. Most of your body is made up of what are called hydrocarbons, which is hydrogen, oxygen together. Of course, water, which is the majority of the mass in your body, is just H2O, just hydrogen and oxygen. And so they by far, there are then what are called the macro minerals. Macro just means big, not that they're large in size, but just the ones that your body needs a lot of. Here are some examples of what they're used in. Take a moment, pause it, read it if you want to. They also have kind of a math there for how much would be in an average human. We then also have the micro minerals or trace elements, which are the ones that you only need a little bit of. The biggest and heaviest, which is iodine. It's part of why you have iodized salt. It's hard to get iodine into your diet, and so we artificially add it to salt. There are some salts that aren't iodized. Your sea salts, they don't always go through the iodization process. Kosher salt does not, but goiter becomes an issue, which is a thyroid issue, and they are only needed in small quantities. A lot of multivitamins have too many of these, and if you overtake the vitamins you need and you have just too much of them in your body, generally speaking, just gets rid of it as waste. Anyway, I think that is most helpful to see here in this form, where you have the major ones that make up your body, the macro minerals there, and then the micro ones. And you can see down here, iodine is the only one you need in large quantities. And that finishes section 2.